And anything that I give you, what I'm looking for is just an honest effort and good old-fashioned honest feedback. When we go out in the real world, the working world, what you're going to be doing is telling your supervisor, you know, this is what I know how to do, this is what I don't know how to do. I'll be happy to do anything you want to assign to me, but I need some examples of what you're expecting from me, some, you know, what are the kind of deliverables that you're expecting from me. Give me some examples of those, and give me somebody to mentor me. That's the most important thing. When you meet people who are very skilled in their craft, whether they're a shoe shine person, which a lot of those have gone on to become admirals and generals, believe it or not, or you're an engineer, or you're flipping burgers somewhere, what you find is that high quality begets high quality. So people who are really good at something are usually because somebody mentored them. Somebody invested time in them and showed them how to do something, and they learned good habits, good skills. And the people that bounce around a lot, that always tend to get laid off first, are the people who are the least versatile. The least versatile people are the ones that always come back to you and say, "How'd you expect me to do that? I don't know how to do that. I never did that before." You know, so you're going to say, "Oh, geez, okay, I can't give it to you." And that's what they want. They want you to shuck it off and give it to somebody else so they don't have to do it. If you've ever raised teenagers, you're going to learn all these things. You know, "Can you please empty the dishwasher?" "Oh, man, you know, I don't know if I can do that. You know, that's... I'm supposed to watch the eclipse tonight for my science class." "Yeah, okay. Well, do the dishes, then do the eclipse." So there's other people on the other end of the spectrum who will tell you, "Oh, I know how to do everything. Don't worry, I know how to do it." And then they don't. What do? They're BSing you, and then they're going to go off and run. They're very insecure, and they're going to go run off and try to find somebody else to lean on and say, "Hey, how do you do this? I don't want the boss or the prof to know. I don't know how to do it." And then sometimes those people get irritated because you only see these people when they're hitting you up for something. Now, I have a lot of people I know in this university and in this town that they're my fair weather friends. The only time I ever hear from them is when they need something from me. And that's how life works. Now, you're not going to fool people that way very long. You can do that once, twice, or thrice if the IQ is above 100. After that, they're going to figure out, "Hey, I only see you when the door's going that way, and I'm helping you and doing things for you." What's going to go a long way in your careers is service. You look at the people who are the most successful, they are service-oriented. You don't run a company, operate a company, if you're not service-oriented. You're not doing them any favors. You have to say, "Hey, I'm going to get out there. I'm going to do this for you." You know, I had a very well-heeled client whom you all know. He was a Hollywood star. He wanted to fly me out to his place in Santa Barbara this weekend, send his jet for me. I said, "No, I'll take coach and fly out there. I'll get out there just about as fast, and I'll save you about 10 grand. Now, I didn't have to do that. But when I landed, first thing after I got over there the next morning, first thing I got at breakfast was, "Thanks, Dave. I know you didn't have to do that. Thanks for coming, because I really want you here." Well, of course I know he wants me there. He's going to fly his jet out here to get me. He wants you there. Now, it would have saved me 2 hours. That 2 hours would have cost him an extra $10,000. You do the math. Now, when you do something like that you don't have to do, that client's going to remember you. So just remember this. I used to just own the geotechnical market in Hawaii. Anytime they had a landslide, I got called. I was always going over there. Not because I went after the Hawaii market. Lots of guys in LA and San Francisco went after the Hawaii market. The reason they couldn't cop the Hawaii market was they charged for travel time. You want to spot yourself out of the market? Charge for travel time. Nobody wants to pay for travel time. Nobody. So you say, "Well, what about all that time you spent on the plane? 5-hour flight from San Francisco to Honolulu." During that flight, you review files, you read reports, you work on the job that you're going to, you bone up for it so you know what you're going into. And you can charge for that, but you don't charge to sit on your keister. Then when you get there, what do? You stay at the least expensive place, you eat MREs and McDonald's. "What? You have 2 PhDs and blah, charge $250 an hour, and you eat at McDonald's? You're darn right. Darn right. You know why? That's the first thing everybody looks at. Every insurance company, every bank, every contractor will look at your per diem charges. Right here in this university when I travel, they do that. I had them all over me today saying, Dr. Rogers, you never charge for breakfast. Why don't you put something in there for breakfast? Because breakfast comes with those rooms. I go Holiday Inn Express, I get breakfast with it. What about this dinner here? The dinner came with the Marriott that night. Wednesday night, Marriott gives you dinner. I know where all the freebies are. And what do I do with them? I pass them on to my clients. That's service-oriented. A client doesn't know how long it's going to take you to read a big report. You could charge 15 hours, you could charge 3, you could charge 45. And I've never had anybody call me up and say, why did it take you 45 hours to read that 700-page deposition? You tried reading a 700-page deposition? Because you keep going to sleep. It takes a long time. Get through it. No, what they'll look at, what they can all judge is how much you charge for dinner. Did you put any wine on it? How much did you charge for hotel? Did you put any extras on the hotel? Were you watching movies and things like this? That's what everybody knows. Everybody knows what those things, whether you're charging as much as you can or whether you're not charging as much as you can. Now, why am I telling all you this? Because you're not all going to own companies. The reason I'm telling you this is the fastest way you're going to get fired when you go to work somewhere. The people I had to fire, the one thing they all had in common was as soon as I gave them a cell phone, they'd cancel their home phone and start talking to all their relatives all over the universe, even out on Neptune. Run up a bill of $700 in a month. Like I'm never going to look at the phone bill. I got news for you. I have accountants that look at the phone bills. And when they see one employee spending $700, do you think they notice it? Not unless they're blind, deaf, dumb, and in the grave. They notice it right now. And they bring it right to my attention and say, this guy you gave a cell phone to, or this guy you gave the company truck to, he just ran up, $300 in gasoline charges. Yeah, he must have gone down to Mexico City last weekend. I don't know. This kind of stuff goes on all the time. And what does it tell you about that employee? It tells you they're very foolish, they're very immature, and you better watch out because they're going to do something to embarrass you, embarrass your company. They're going to get you sued, and they're going to be long gone. And you better fire them fast with a smile on your face and say, I think you have a bright future, but I don't think it's at this company. It's somewhere else. That means flipping burgers at McDonald's. Somewhere else. So the fastest way to get yourself into trouble is don't be a servant. Don't be a servant. If you're a servant and you're always passing the savings onto the client, they'll figure it out. They're not stupid. People are not stupid. They'll figure it out. And they'll realize, hey, this person's working for me. They're not just working for them. Okay, so that's today's little professional development tidbit. I do a lot of those in this class. We've taken my classes, you know that, because that's the jungle that I come from, the dog-eat-dog jungle. It's actually a fun jungle to work in. So let's go to the homework problem. Hopefully let's see, I don't know how, I got to figure out how to do this. How do we switch on to this so we can look at it?
It's there. It's just on the computer. You can.
Oh, I got to do it on the computer?
We're on the far right there. Minimize the AverVision thing. See that over there.
Oh, okay. Great. Great. And do I have a light on here somewhere?
Yeah. It says mail.
Is that this little thing? Okay. Is that it? What did you hit? Oh. Hang on. Okay. All right. So what we have here is your assignment, one of your assignments for Chapter 3, and it's a geo cross-section. Now, for those of you who don't have much geology background, I got to give you a little explanation. This is a bank excavation for a deep foundation in Budapest, Hungary. So we're in a major river valley, and what you see right here is a strip map of the geology from the floor of an exploratory trench, and that trench was about 3 meters deep. about 10 feet deep. And so what we're picking up here, we're seeing quaternary units. So this goes in line with the section along the south side of the excavation. And what you're seeing here is the geologic units. The Q units are quaternary geologic units, younger geologic age, that cover much older Jurassic Cretaceous units. And then as you go along that line, what I want you to see here is how the strike and dips vary. Here's a 20 degrees, and then you see a whole bunch of, there's an overturned fold, and then there's 60 degrees, 55, looks like 35, then 30, and we got a fold, and then 50, and then here we're going 80 in both directions in the Q3 material, and then 40, 80 in the other direction, 15. If you saw this as an engineering geologist, you just look at this and you go, here's your reaction. On a scale of 1 to 10, this is a 10. You're going to go wild. This is wild. Things are going. And if you got things that are folded, you got any kind of folds, you're not going to be able to play the, let's put a boring here, and let's put a boring there, and get a ruler and draw straight lines between them. Not going to work. There's no amount of rulers and drawing straight lines between the borings going to work here. These 4 borings are like a boring in Antarctica, one in North America, one in Australia, and one in Central Asia. That's how well they're going to correlate. So I just want you to know that. So what I want you to do, I want you to put in a fair effort. Now what I show here is the cross-section. Sorry about this. I got to turn my phone off. What I'm showing here, I'm going to turn the phone off, is a cross-section that was done by the project geologists. Now these guys probably had 20 years of experience when they did it, so they're not stupid at all, and they know the local geology. And they've worked in this area. Now that's essential on engineering geology. You do somebody who's from out of town, somebody who hasn't worked in that area, you're not going to guess it right, most likely. You're probably not. There's going to be a lot of learning curve that goes on. So it's always dangerous to use geotechnical consultants when their geology comes from some other area. Now, soil mechanics and foundation engineering is not that way. It's all very codified, very cut and dried, put into nice little Betty Crocker cookbook formulas that apply universally to the whole world. That's great, because concrete is pretty much, you can make the same mix of concrete anywhere you go in the world. You can't make the same foundation under the building anywhere in the world. Every single site is going to be different. Even if you're in the same geologic formation that you were over that county or over in that state, the stress history is going to be different because of the geomorphic evolution of that area. Okay, so just because you're in a formation doesn't mean it's going to behave the same. Formations are glamorizing big, huge things like Native American. That's a big formation. But are all Native Americans the same? No. No, you got lots and lots and lots of differences. You're going to have nuances, even within a single tribe. So this was their best guess. So what I want you to do is look at those boring logs. There's 4 boring logs, and see if you could come up with an alternative explanation to theirs. Okay, that said, I don't want you to burn up more than 90 minutes on it. Don't spend more than 90 minutes. Get the 90 minutes, stop, and give me something. Give the boss something. Don't give the boss question mark, I couldn't figure it out. Do something. If you can't do anything else, you can trace what's there already to show me that you put some time into it. Okay? Because that's what your boss is going to look for. Now what most bosses look for, and I forgot to do when I was young, they usually look for a scale bar. So if you're going to go out there and you're going to draw anything in the field, you either got to put a scale in the picture and photograph it. I always used a meter stick. And on the meter stick, I actually put on the lower 50 centimeters, I actually had black tape up and down, so I could see that thing, 5, 10, 15 meters away. I could see my meter stick. And then you have other things you can put in your pocket that are centimeter sticks and inches that you can put down and photograph. But you always want to have scale. You have to have context. When you're looking at geologic structures, context is everything. So either you get a bulldozer or something in the picture with it, or you get a scale bar in there. Now, if you draw something like this, usually you want to put a scale bar across the bottom. You also would want to say what the trend of the section is. north 90 degrees east, or east-west would be the trend of the section. And here you can see what they have is they have the depth in meters marked out from 36 down to 14. And I would imagine it's vertically exaggerated, but we don't know how much. So it probably is vertically exaggerated. Now, typically what we do on that kind of thing, let's look right here, we would put a little bar like this, and this might say, 2 meters, and then this direction might be 10 meters. So we'd actually put in a little thing like that. That tells us that we have a 5-to-1 vertical exaggeration. We put that little kind of thing in. Or we might just put in some kind of scale bar like this that has what the scale is. And then you might say in feet or meters, whatever you want to do. So, but generally, you've got to have something there that gives people an idea, at this depth and this kind of layout, this is what I expect to see. Now, these things are important when you're characterizing a site because people are bidding the document. And the bids are always going to be higher if there's more geotechnical uncertainty. And when you get geology and folds involved, you're going to get a lot of geotechnical uncertainty. So if we fold something, let's say we have some sediment, it's laid down flat, and we're going to start compressing it. When we compress this the slope of about 10 degrees, it'll start faulting. You'll actually start getting faulting along major contacts. Let's say we have this contact here. It'll actually squeeze upward. So this wedge has to squeeze upward compared to the wedge under it. And as you keep folding it into a syncline, you're going to have all sorts of faulting coming out of this trough that's just wild. So you're going to get fault, 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 fault like this. And you get into axis. These are called out-of-syncline thrusting. I worked one case once out in California. It was IT's hazardous waste site, Panoche. We had 200 of those faults just underneath, within a mile, underneath that haz waste repository. 200 of them. You just could hardly count them. There were so many. And when you're going across the axis of a squished-up syncline, you're going to see strike and dips go back and forth. Sometimes you'll be 85 this way and then 85 that way. So you're going to get overturning. You're going to get a lot of variation in strike and dip. So this stuff that these teaching assistants do with you in field camp, where they take you out and try to get the strike and the dip within a quarter degree, that's sophomore-y stuff. I mean, the real world, you got a lot more variability than that going on. And if you're up on a hillside, none of the strike and dips you're going to take are going to be representative of what's going on down in the ground because you're influenced by slope creep out there. So you can get into a lot of trouble taking a strike and dip right on the side of the hill and then projecting it down with a straight edge. You're going to be wrong. You're going to be wrong most of the time. So you got to be real careful about that. So you wouldn't project that into the hill with a solid line, because people are going to look at that and say, well, that's not what we found. We got out there, so you obviously did it wrong. Okay, so does that give you some background on this little exercise? All I'm trying to show you in this exercise, once everybody turns it in, then I'm going to give you the answer. Be very nice and gracious of me. I'll give you the answer. So nobody can do it wrong. I just want to see effort. I want you to struggle with it, because then you'll remember it. And you go, God, this guy gives hard assignments. Well, that's probably the hardest one I'm going to give you the whole semester, okay? But what I want to impress upon you is very difficult to draw cross sections if you have folded geology underneath you. You better watch out. It's almost impossible to draw an accurate section, okay? So that's what I want you to get out of that exercise. Now, some other things I want to look at as long as we have this thing up right now. Let's see. How do I zoom in on this? Well,
Guess you don't. What I want to impress upon you is in weathering, it's the most important chapter we're going to talk about in here. And some of the things we're going to talk about, I'm just kind of showing you some examples here. And that is, there's a high degree of variability in weathering. If I do a boring right here, or I do a boring right down here where this shear zone's coming out, I'm going to see bedrock way down here in that boring, and bedrock contact way up here in this boring, only a meter away. So there's a high degree of variability when you're dealing in residual soils. This is kind of the situation that we have all over the Ozarks. We're a karstified area, high degree of in-place weathering variability. So it can be very tough to, again, construct reliable cross-sections solely on boring data. You'd want borings and geophysics and trenches. And even then, you'd want to give yourself a pretty healthy buffer saying, well, this is where the bedrock was in this boring, but it could be a couple meters below that, or even more than a couple meters below that. Down here in the lower picture, you see floaters. We call these knockers. These are old core stones. And as this weathering surface gets older and older, goes down deeper and deeper, we get these isolated core stones or knockers. And so we drill a hole and hit one of these things. It can stop the drill very easily if we're using just continuous flight augers or cone penetrometer test. And we could come to a very erroneous conclusion about where the bedrock contact is. So, whoa, you got to be real careful. So, like I told you last week, MoDOT, Missouri Department of Transportation, if you're going to call something bedrock, they require that you core 10 continuous feet into it. If you don't get 10 continuous feet in the core barrel, because you didn't recover the 10 feet, well then you got to go another foot or two till you get 10 feet of core before you could say, well, that's where the bedrock is. That's because MoDOT's been burned so many times by these kinds of situations. So this is something I want you to start thinking about and looking at highway cuts. When you go by highway cuts, let somebody else drive or stop and look at the variability of the weathering profile in there. And the big thing you want to watch out for is right here, is what I've shown here, and that's shear zones. There's a shear zone. Here's a little diagonal shear zone. Shear zones are going to have a lot more weathering, more severe, deeper, because they're groundwater barriers. So you're going to have more oxygenated groundwater, more ability to have cation exchange and promote chemical weathering, and you also get more mechanical weathering, because if you have water going down there in a road cut and that water freezes or that water thaws, you're going to get more flaking off of material. So this next picture I'll show you is just typical kind of highway cut problems I would see all the time, where you see the material sliding off the weathered regolith above the bedrock. So here's the oxidation weathering line, which is greatly influenced by rock joints, because the water is traveling down the rock joints. Rock joints are interstate highways for water, and all the weathering occurs along the interstate highways. So the joints are the most important thing out there. The biggest difference, I got asked this last week in this meeting I went to out in Santa Barbara, so tell us, Dr. Rogers, what's the difference between a geologist and an engineering geologist, or a geological engineer and a geologist? Well, when I was a geologist, our focus was on petrology. It was on mineralogy, diagenesis. A lot of it fed to the mining industry, economic geology, and to the petroleum industry. But when I crossed over and became an engineering geologist, then we started talking about material properties. We're starting to look at things more like a mechanical engineer with a solid mechanics background. Solid mechanics, what you're going to look at is fractures. Rock is a sugar cube pile. The only question is, how big are the cubes? Are they equidimensional? Hardly ever. So they're never like a sugar cube pile in that respect. Usually one joint set is more domineering than another one. And usually you have three of them. Sometimes you have a lot more than 3 sets, but typically you'll have 3 dominant sets plus foliation or bedding. So you got 4 things going on that you're trying to gauge there. And with joints, you got to be real careful about just taking 1 or 2 attitudes and then showing them on your map like you do with bedding, because joints have a lot more variability. You'd have to do 10 or 12 measurements and take the average to have it mean anything statistically. And then it can change, too. So what you want to look for is how much does it change? So you do enough measurements to see how much it changes. So you plot on your pole plot, you plot the mean point. But then what's important is how much can go that way and how much can go this way. Because it's those exceptions that burn you in the road cut failures. The road cut's designed for the median value, because that's the way engineers do things. We got that nice structured part of our brain, remember? We like to do things and say, ooh, I love numbers. What can I do with numbers? You can add them up and divide them to get the mean value. Oh, we all love doing it. Engineers love doing that. We love mean values. Mean values are nice to us, because then, isn't that a paradox? Then we use those to design it. Now, obviously, in the places where it's not mean, the mean value, where it's worse, it's steeper, those are the places where it fails. And you go, oops, we screwed up. Yeah, you screwed up because you ignored that low end of the bell curve. And you got burned. Ouch. Yeah. So that's judgment. So the test that really works, the best test, is to walk along the creek channels, walk along the old highway cuts, walk along the old railroad cuts, and look and see how things have performed. That's going to mean a lot more than any computer output and any theoretical analysis you do. And what you do is you go out there and you look at the wedges. This is what I was doing this weekend in Santa Barbara. I'm looking at these, these big wedges, and then I'm going to do back analyses on those. And those back analyses are going to tell me what kind of numbers I should be using. And what I found out in Santa Barbara was, it's all got to be pore pressure. These things shouldn't be falling down the way they're falling down. So there's obviously got to be some pore pressure issues involved, trap pore pressure. And sure enough, on the block that had just recently come out, like 4 days before I got there, and it was a big one, about the size of this room, you could see behind it all these lines, looked like jail, like bars. And when you got up there closer, you can't get too close, it's an active rockfall, and you look, those were leached joints. So oxygenated groundwater's percolating down these very tight joints and leaching out about a 1/4 inch either side of them. So that's telling you that water's been flowing through those joints. And what we're going to learn about water is it's not about the volume of water. You won't see any water coming out of those joints. It's not about volume. That is a myth. It's about pore pressure. The thinner the joint, the more tight it is, the more easily it can get saturated. Once it reaches saturation, you got pore pressure, 0.414 psi per foot. Now we got a cliff 200 feet high, so you get some pretty healthy 75 psi. That's plenty to pull any block off. That's way more than enough. Times it by 144 to get PSF. Big number, real big number. So it's not about volume, it's about pore pressure. If you can alleviate pore pressure, you're going to alleviate problems. All right, so here's another one right here on the lower end I want you to look at. Real typical, where you see the weathering lines going way down along fracture zones, coming back up, very highly undulatory. You see big color changes. This is real world stuff, real world stuff. And then you see a dry season groundwater table, GWT, a wet season groundwater table. See, when that water table comes up, you're going to start seeing seeps and springs and problems that you haven't seen before. So a lot of time, we call this now in the geology world decadal cycles. Decadal cycles means you have enough data over enough decades to look at decade-long cycles. And what we're realizing is it's the decade-long cycles that are really important. Because if you have something wet over a long period of time, all of the trapped air gets pushed out, and you lose your negative pore pressures, and when you get all that air gets expelled out, the crap hits the fan. Because now you're saturated, and you can get a world of hurt that you'd never seen there at that road cut for the previous 30, 40 years, because you finally have reached true saturation. And you just run an infinite slope analysis with pure saturation, you'll see how little it takes to make it fail. You're lucky if you get a phi of 20 on the back calculation. And the cuts, of course, 26 or steeper. So that's why it comes out, down about a meter deep. Here's another one, weathered road cut. They came in and cut the bottom off of it, destabilized this gravelly conglomerate layer here. Now, conglomerates are very, very strong. The problem is they're aquifers. So they got lots of water moving through them. And what I want you to do now, whenever you drive around, you see a gravel unit, I want you to look at the bottom of it and tell me what you see. Because what you usually see below the gravel is something like siltstone or shale. What's the permeability of siltstone or shale? Well, it's 2 or 3 orders of magnitude lower than the conglomerate. So what happens is you get pore pressures perched on the base of the conglomerate, and you get seep undercutting at the free face. And so the conglomerate's very strong, but its foundation has high pore pressure, low friction, and it's slipping out little bit by little bit. And the big strong stuff above it, after it gets undercut, has very low tensile strength. Conglomerate doesn't have high tensile strength, but it has a lot of cementation, and the blocks just fall out. So your slope's only as strong as the weakest link. The shale seams are always the weakest link. Always, always, always. Okay, we're going to stop at that place there today, and we'll go back over here. I got to figure out how to get us. How do I get off this? Go there. All right. Nope, I didn't do it. I want to minimize that.
That's it.
Open my PowerPoint.
Yeah, stop sharing for a second.
What? Okay. Okay. Now you're going to have to remind me where we left off last week, because I'm getting to that age where I can remember how to get to school and where to park and where my office is, and it starts getting foggy after that. So we got down.
Part 4.
Okay, part 4. All right. Spheroidal weathering. All right, so we're going to start on spheroidal weathering, part 4. This is an interesting case right here. This is called globe rock. Globe rock had a big sign in front of it when I first went out to look at it, and it said, "This is a classic glacial erratic." This is my brother-in-law and my oldest child right there, and it's the summer of 1981, and I went out here to look at this. It's a granodiorite, and I noticed an albite bed, or vein of albite, about 2 inches thick, running through this boulder, right through, connecting with the pedestal. And I said, I think that sign over there is wrong. I think this thing actually weathered in place. It's a core stone. And being a rock climber, and this is just south of Yosemite National Park in the Sierra National Forest. And so I mentioned this to Jerry DeGraff, who was the Sierra National Forest geologist, and he went out there and looked at it and came to the same conclusion, and he changed the sign. So spheroidal weathering is something we see all over the world. My favorite place to hang out when I was in college was Baja, California. And the reason was simply economics. It was the great untamed wild, wild west. Lots of banditos, and you could take $100 and go down there for a month. That was a pretty good deal. I mean, you can't find a better vacation deal. I guess you go to Walmart parking lot and watch things going on there for less than that. But yeah, you see a lot more interesting stuff down in Baja. And the geology is a lot more interesting than the asphalt over here at the parking lot. And Baja California, this is where this picture is taken, is a Southern California batholith. So it's lots and lots of Jurassic age granite, most of it around 50, 55 million years old or so. And you have these big core stones that are weathering out, and they're all joint block border. So the core stones are a function of the joint spacings. So if we look at that, granitic rocks weather as the ferromagnesian minerals right here decay. And they decay first because they are the furthest from their environment of deposition. So you have them weathering first, the dark minerals weather first, followed by the feldspars, and the quartz particles that are in the granite are the part that is the most stable. And that's why most beach sands are dominated by quartz particles, because you can't weather quartz down into anything. It's as stable as it can be. It's SiO2. Now, one of the most unstable things out there is olivine, SiO4. Very similar, but 2 more oxygens on it, so more reactive. And the oxygens get pulled off. You rarely see olivine or peridotite out there anywhere. It's usually weathered away and gone. The Kona sands on the Big Island of Hawaii are all olivine sands. That's the only place on the planet I know of anything like that. So carbonic acid from rainwater, and rain is slightly acidic. And if you run that rainwater through decaying organic matter, it gets more acidic. And those percolate through the decaying forest litter and weather the feldspars and the calcite. Calcite's limestone type stuff. That's highly soluble compared to feldspar. So these things get weathered, and we tend to get kaolinite coming out over here. And so kaolinite's been studied a lot in the soil mechanics literature, especially by Norwegian Geotechnical Institute. Back in the 50s and 60s, they kind of use it as their basic neutral clay. It has very, very predictable properties, and you can actually mine it in very pure form. We use it in California for our has waste liners, and I used it in all of our firm's work to do a low-level nuclear waste isolation for the Department of Energy. And the reason we use it is because it has very predictable properties, and we could purchase it in pure quantities, large quantities and very pure, 100% pure kaolinite. And it still desiccates like crazy, by the way. That was the hardest thing we ever tried to compact. And going into the job, we knew it was going to be a challenge, but I was very overconfident because I grew up in the grading business. You know, I know dirt better than anybody. I'll just have 2 water trucks out there, you know, watering it continuously. And they said 24/7. I said 24/7. We're going to have the Klieg lights on. We're going to do this waste isolation pits. You know, we're going to get it all done for you. And boy, did I get my comeuppance. I forgot we were in Altamont Pass. Altamont Pass has wind. And wind is a much bigger factor than air temperature. Wind will take water out of a soil way faster, as fast as a microwave. Yeah, that's pretty fast. Woo! Yeah. And so we're standing there, we're just watering the heck out of this surface. Water truck, and we're watching the desiccation cracks growing right before our eyes. I wouldn't have believed it if I hadn't seen it. So there's always going to be things in your career that are going to surprise you. I guarantee it. No matter how smart you are or how smart the people were that mentored you, there's always surprises. And that's what you want to keep your eyes open for, the surprises. That one scared me. I got to be real honest with you. It really did. Because we had everybody in the whole country watching us doing the thing. Weathering halos. One of the things you learn as an engineering geologist is go out and observe weathering features. Here's old exfoliation joints, and you got all this iron staining from the ferromags and the feldspars. Really, really rotten rock. But you can see along the joints here, everything's just gone. You got a 1-inch wide gap. So water's traveling down this thing like the interstate highway. That's like the Panama Canal. And water's percolating in from these bounding joints. And then anywhere where there's an old joint surface, you're going to have the micas are going to hydrate. And we call this hydrolysis of the feldspars. And that's all from the groundwater percolating through the specimen. And you'll actually see mineralization halos like this. That's really, really common. That's a mineralization halo. And this orange stuff here is hematite, and the yellowish stuff is limonite. Limonite's a tough one to pick up and identify because you don't see it on X-ray diffraction. It's amorphous iron oxide. It's got one more oxygen in it, so it doesn't show up on XRD. Hematite's a breeze. But you pick up hematite easy and know that you have it there. Limonite is much more ubiquitous, usually in lesser quantities, but harder to identify. Now, what's important for us as engineers? Right here, the last statement. The strength of the ground mass is significantly affected by all this weathering stuff. You've changed this from being a very hard rock that would be very difficult to excavate. This outcrop I show you right here, it has snow on it. That's what all the white stuff is. Any of my Cat D6 series and up with triple ripper, take care of that, no problem at all. That'd be like eating an ice cream cone for a teenage boy. Not a problem. Just rip it right out of there. It's not going to be a big issue because it's so weathered. Now, you ask the geologist, what do we have out there, Frank? What kind of rock? Granite. Now, as soon as you say granite, everybody in this room is going to think of something. Some of you are going to think of, Yosemite National Park, El Capitan, 3,000 feet high, really strong rock. Well, granite runs the gamut from Grus, you can just pull out with your hand, to stuff that's 3,000 feet high and glaciated. All the weathered rock in a glaciated area has been carried away by the glacier. It's like a giant Hoover vacuum cleaner. All the bad stuff has been sucked up and taken out. It's not there. So glaciated surfaces, you get up working in the Alps or you get working in Scandinavia, boy, they got hard rocks. Man, you don't see weathering rocks anywhere. All the weathered stuff's been hauled off and eroded by the glaciers. So when you say granite, that doesn't mean anything. You got to put some modifiers on it. We got some weathered granite. Now, the other problem is you could go 9 meters down right here, and it might be fresh and hard, and you can't rip it with anything. That's where the problem usually occurs. We tend to group things based on petrology, and we don't describe them very well according to their mechanical properties. But as engineers, that's what we're concerned about. We're concerned about their excavatability and their mechanical properties. Here's one at the Tom Sauk Dam failure. It's a classic picture. I'm looking at 3 lines of core stones. 1, well, actually 4. 2, 3, 4. This is Ameren's chief geologist. This core stone is in granite, and it's completely intact. There's the master joint. The stuff filling the master joint is just grus. It's soil-like material. It's weathered in place. Then we got a core stone here with a grussy type of stuff underneath it, and we actually getting more weathering as we go down. Then the same thing right here. By the time we get over here, this is just soil-like material. In fact, this is gone now. This didn't even last 1 year. It just disintegrated and fell apart. So if I drill a hole here, or one here, or one here, I have 3 completely different sites. That should scare you into becoming a structural engineer. See, that's the key of our business. There's a lot of judgment that's going to have to be required. And you have to realize that conditions can be highly variable on a local scale because of weathering. Here's another view, not too far away, and we're looking at here is a diabase saprolite. Now, the diabase is what caused all the problems in the Tom Sauk failure. The diabase is a very basic intrusion. It's like basalt that came up from the bowels of the earth, and it intruded into the country rock. And this material weathers, back in the Precambrian, it weathers much more rapidly than the more felsic types of materials, the more rhyolitic end, because this is hot stuff. And they didn't identify all these diabase intrusions when they did the project, and they got out there and started digging, and they got this rotten rock. What do you do with the rotten rock? Well, the spec says you're supposed to waste it. But if they waste the rock, they can't do the project on time or on budget. So they wasted quite a bit of it, but then they decided they were hitting so much of it that they would just incorporate it into the fill, and so that's what they ended up doing. Now, when they did the Tom Sock rebuild, hit the same formation, they had to go down over 40 feet before they could even get to a weathered diabase saprolite that was good enough to put a gravity section on, Roll Creek Dam section on. So the diabase intrusion, you can see here, this is a relic joint bed, big, huge joint bed. This is Professor Ronkowitz in the geology department. He's a clay mineralogist. And then you can see all these little joints cutting through it. Those are the joints that are parallel to this surface right here. And that surface right there, same joint set. Step down a couple feet, same joint set. So you got a major joint set here, which is the same one as that one. You got a major joint set here, and then you have all these smaller ones cutting into the plane of the picture. So that's jointed material. Well, when you walk up to it, you could just sink your hands right into it and just pull it off like modeling clay. Uh-oh. You mean doesn't behave like rock? No. Behaves like clay. It's rock weathered in place that behaves like clay. That's the kind of stuff you got to be watching for. Just like a banker watching for bank robber, casing out the place. That's the kind of stuff you want to watch out for. Saprolite. Here's core stones in a saprolite. Core stones just mean the weathering starts from the master joint. So along here is a master joint. Over here somewhere is another master joint. The water travels along the master joints like the interstate highway, and then the water seeps in if the water's under pressure head. So one of the things that's very, very debilitating about running constant head permeability tests over in the soils lab is all of you think that that intrinsic number you get out of there means something. What does it mean? It means that under a differential of 1 or 2 psi, this was the hydraulic conductivity. 1 or 2 psi. Yeah. Is that a significant number? No. That's like me trying to do a direct shear test by taking my little pinky and going, it doesn't move. It must be strong. Well, what are you talking about, Rogers? What I'm saying is, if you put 1,000 psi pressure differential, you're going to get a much higher figure for hydraulic conductivity. That's what you have going on in the mountains. You got a mountain 3,000 feet high, you got over 1,000 psi pressure pushing through the joints. You push a lot more fluid through under 1,000 psi than you do under 1 psi. So it's amazing. You have to always look at head. Pressure head is your enemy. Pressure head, all that pore pressure is going to reduce the normal effective stress. So pressure head is very, very important. So we got this water traveling through these joints, but it's under head, so it actually gets pushed into the rock. And as it gets pushed into the core stone, you're going to see stuff like this. You're going to see weathering halos. And this one is rotting from the inside out, actually, in this particular case. The bounding joints are way over here. Here's a bounding joint right there, going across like that. Here's another one right up here, going like that. And here's another one. And what you're seeing here is this onion skin kind of texture is because you've had hydration of these materials from this water seeping in under great pressure, and it has a cation exchange with those materials, and it's basically weathering these materials into clay-like materials, in this case right here. This is the weathered saprolite. These are both granite, and this is a granite one, this is a diabase one. This diabase one, you can see it's very, very punky material. Punky material means it's all passing the number 200 sieve. So that's not a diabase anymore, it's a soil. It's a plastic soil. All right, here's another one where I'm on a road cut out in California, and where I don't have humid weather, but they used to have humid weather there. And I'm in the Sierra foothills, and I actually have a road cut, and this is a pegmatite dike. Pegmatite coming down like this. And this is a decomposed granite, or DG, just Grus. Grus is a term that describes siliceous sand and gravel, granule gravel, derived from the weathering of this granular material. And it's just, you can just run up here with your hand and just pull the stuff off. Now, Grus can be pretty strong as long as you don't run running water against it. If you take a fire hose and run it against this stuff, it's going to start eroding on you. No question about that. So it has some cohesion, but not a whole lot, especially out near the ground surface where there's freezing and thawing going on and relaxation from being unloaded by the cut being excavated. So in the grading business, we call this DG. That's a slang term, which means decomposed granite. Now, once again, decomposed granite runs the gamut of, from over here to over there. I've seen it used to describe something that's completely saprolitic down in Panama, where I couldn't see hardly any relic bedding at all. And it just behaved like a stiff soil. And then this would be the other end of the spectrum, where you can actually see that it's granite, but you can also see that it's lost its unit cohesion. There's no way this stuff is going to, you're going to take a core of it out and get, 2,000 PSI compressive strength, like a sidewalk concrete. No way. It's not that good. Now, if it was on a nice flat site and you put a big load on it, you might get 30 tons per square foot on it. No problem, because there's nowhere for the failure to go easily. But on a slope, you could have trouble. Well, here we are back to Baja again, and we're looking at granitic blocks. And again, now you see where the analogy to a sugar cube pile. We can actually see these master joints cutting through at an angle like that through here. And you can see all these core stones, the largest ones being right here, large group of core stones, because the regional systematic joints here are further apart. So you get your largest core stones in that area. These other areas, the core stones are falling off and they're smaller. And so you get quite a variety of block sizes. And these things naturally round themselves. So if we look at a telephoto lens, we get up there and look high up on the slope, you can see the controlling joints there going like that, coming down and crossing each other acutely. And you can see this core stone orphan that's just sitting in this block. That wasn't put there by an ancient Indian landfill. It's just natural. So you have water traveling down the joints, and then you have mechanical weathering that's occurring adjacent to the chemical weathering that's occurring along the joints. And the mechanical weathering is what we call exfoliation. So if we look at one of these core stones, I'm standing right on one now, down in Baja, and I'm taking a picture with my camera looking down, and what I see, I'm standing on a nice big block of granite, and you see all these little onion skins. They're about quarter inch apart, half inch apart, just one after another, after another, after another. I don't know, maybe 12, 15, 16 layers. But that's on the outside of this core stone. Now, when you take a thin section through here, which I've done a lot of those to see, hey, what's going on here? Because we use these in rock climbing. This is what we climb on, these exfoliation joints. When you take a thin section and you look at it, you see the micas are hydrated. So some of this is the hydration of the micas absorbing water and increasing in volume and pushing the thing out. And oops, I went the wrong way. And some of it, what did I do? Some of it is actually.
You can just click on share desktop. No, don't hit that.
Oh, sorry. What did I? Okay. I did something wrong. Tell me what to do now.
Okay, I think we just need to get back from share desktop.
Okay. Sorry. I don't know how I even got on that.
Don't worry about it.
That's because we're webcasting it out. That whole thing. Okay. All right.
Yeah, if that pops up, just hit share desktop. It's an icon that should up here. But I didn't think you had left the meeting, so. Awesome.
So we're okay?
No.
No. Oh.
Hang on here.
All right. Should we just take a little break right now? Let's just do that. Take a little 5-minute break right now. We're going to go all the way to 6:30 today because I'm not going to finish the course with you because we lose Labor Day next week. Okay, notice in the notes here that I put there, the onion skin exfoliation of core stones driven by hydration expansion of the micas, release of residual stresses, and thermally induced strain. So you got a number of different factors that all combine at one time, as we discussed last week. Here's spheroidal weathering of a granitic core stone. This is pretty typical what you see on a Forest Service road where they're logging an area. We're in decomposed granite. And in this case, we got a rine on this block that's extremely weathered. You can see this stuff here. You got about 6, 7, 8 circular joints, and this stuff is just really cruddy, bad stuff. And then the core of the core stone is very, very hard. And they had to come in here and jackhammer that to break through the core stone to just make this little road. And over here we have core stones that are left intact. They didn't have to cut right through the middle of them. So this is like cutting an orange right in half, this core stone. And you can see it's very, very circular, which means we have equidimensional blocks, or more or less, which isn't very common in geology. Usually everything in geology is euhedral. Usually you're longer in one direction than in another direction. But in this case, this is, again, nice granitic rock up in Washington State. Here's another one where I'm driving by in my Jeep in the old days, and there's the ground surface. We're in an area that's been glaciated here, and so the glacier came by and just chopped everything off. And so we got a zone here about, 2 meters deep that's really, really weathered all the last 14,000 years. But here we are, we're going right through a core stone, and there's your depth of severe subaerial weathering. Wow. Cuts right through the thing like a bandsaw. And here's a block with all these circular joints, fairly intact, pretty good stuff. But right there, boom. And there you got about as smooth of a weathering surface or change as I've ever seen. So, we would call this sea horizon material right up here, weathered bedrock in place. All the structure's gone, you notice. Can't see much structure. Down here you can see a lot of structure. The rock's weathered, but nowhere near as much as right up here. So they're really like two different materials, same core stone. The weathering goes right through the core stone. Globe rock is a core stone that actually formed in situ. Now, in situ means in place. So this pedestal was actually part of this. This had a joint going down right here. There was another master joint going down here. The core stone got left. You have another joint cutting right through here, the bottom, and one across the top. This area severely glaciated and just happened in this little bench area to have left this core stone in place. And the dark colored stuff on here is manganese and ferrous oxide. So you actually could do a cosmogenic date on this block if you wanted to get a date. You probably get something like 6,800 BP, something like that. Be my guess. Probably right in the middle of the Holocene. Here's Elephant Rock State Park, which is right here in Missouri. And Missouri's got one of the oldest erosional surfaces in North America. It goes back to the late middle Miocene, or upper middle, we call the upper middle Miocene. And in this case, we have all kinds of spheroidal weathering in these very, very old Precambrian granites. And the pink color is the kaolinization of the feldspars. And then when you walk around on the ground, a lot of that gets worn off, and we actually see more of a gray color just because it's being touched and worn off all the time. And these are lichens, these greenish, yellowish things here growing on the rock. Lichens secrete very acidic enzymes that eat into the rock. And when you go to Air Force or Navy survival school, that's one of the things they teach you, how to eat. And they tell you that they taste like scrambled eggs. I went on one of these 5 days, you get shot down and they come out with the hounds and try to catch you. And I was darned and determined, being a track and field man, that they weren't going to catch me, because the first day I was going to put 30 miles on them. And I figured they drop these flyers off and they figure, what are you going to move one day? Maybe 10 miles a day, expanding circle. And sure enough, I stayed ahead of them, and I had to live on lichens. Now, you really should do that for a week. You should go out and try to live off the land for a week, because your young wife's cooking is going to look really good to you the rest of your life. There's nothing she's going to burn that's going to be as bad as eating lichen. It does not taste like scrambled eggs. And rattlesnake does not taste like chicken. It tastes like puked up snake. That's why I don't go anywhere without a couple MREs in my car. Hit away, man. I don't want to do that again. Thank you. Glacial erratics are large fragments that are transported by glacial ice like this. I remember telling my aunt once, she worked at this nature preserve up north of Grand Rapids, Michigan. I said, see that big block of granite there, Aunt Pris? Yeah, I said, that came from the Central Canadian Shield. She never believed me. She couldn't conceive of something so ridiculous. She thought I was just pulling her leg, because I did pull her leg on a lot of things. But that one I wasn't pulling her leg on. Granite with pitch blende in it. That comes out of the Northern Canadian Shield. Pitch blende is very radioactive. That stuff all got brought down on glaciers that were more than a mile thick. And so glaciers love to move stuff. I don't know what I did here. I'm hearing people talking. Click on share your desktop. That's what I'm doing. Time for technical help.
You're telling me to add this, I'm going to use this and it's going to add to 6,000.
Well, that's,
No, I'm saying you can add this up, it's going to be 12,000. Your difference is going to be...
If we're going to listen in on somebody, make it something kind of neat, okay? Maybe risque, type thing.
Same way we've done all the others.
Call me at a new number.
Honor just became presenter for no reason.
So you're saying just take the difference from each one. You do hardly any other one. No, it isn't. I did it the exact same way. I copied the...
All right.
I was able to... I copied and pasted the form.
I didn't do anything that time. I didn't click on anything.
No, you didn't.
I don't think you did anything the last time. We just got a bunch of emails from our other coworkers
Yeah.
having similar problems.
Oh, okay.
It's just going on with WebEx right now.
We had a symposium I was part of this summer, ex-Navy flyers down on the USS Midway. Each decade was talking about, what your experiences were flying. And my decade, I started in the 70s, we were flying war-weary McDonnell Douglas F-4 Phantom to reconnaissance aircraft. And I don't ever remember flying a single mission
Thanks for using WebEx.
where
Please visit our website at
something didn't go wrong, where some system didn't work. And the young guys, my son-in-law, being as a young Navy lieutenant commander, his first command right now, they're listening to me going, wow, I can't believe that. I can't imagine, going out and having the radar just fail on you. How do you get back to the ship? What did you do before Magellan's? You drive around and you look, going, Kentucky Fried Chicken? Where are we going here? You learn how to do things like that, So one of the ones I always remember is drillers. Drillers tend to break down, and they waste all your money. You get out there and they break down, and you go, okay, I've only got $5,400 for drilling. That's just today. And this guy breaks down on me at 2 o'clock. What happens with drillers is you learn real quick. The ones who break down all the time, you can't afford to use them. And you just have to say, well, been nice doing business with you, but you're not reliable enough. Because for them, it's just money out of their pocket to be down. But for you, if you got to come back out the next day, it's not in your budget to come back out the next day and finish drilling the site. So they can just kill you. So you learn to be very, very choosy on who you pick. Now, the system that I use is a biblical one, and that is you pay people the day they do the work. And I found that most people really like that system. It means if I show up today, I'm going to get paid at the end of the day? Yeah, that's what it means. And if you do that, what will happen is, and I always did that, when my clients would ask me, what's it going to take to get you out there? I said, it's going to take a retainer. Oh, they don't like the word retainer. What does retainer mean? It means money up front. So it means I'm charging you $11,000 to do this job. I want a retainer for $5,500 up front. And that's a great litmus test to see if it's a client you want. So a lot of clients will say, why do I have to do that? So-and-so doesn't make me do that, blah, blah, blah. You say, well, I pay my subs my driller, my surveyor, you know, whoever it is, my water test guy, my lab guy. I got to pay those guys right up front. I can't wait 6 weeks, 10 weeks, 12 weeks. Like this university, I taught a distance course last January to April. You know, they got the money for that course. Every one of those people don't get into the course until they pay the fees. So they got the fees on January the 6th. I still haven't been paid. I'm not going to get paid even on September the 1st. I might get paid earliest is October. So that's 10 months they've held on to the money. How do I feel about that? You can see how I feel about it. Not too good. So what do? I pay these guys the day they show up. So what I heard over the years, I never had any trouble getting subcontractors to show up on any of my jobs. In fact, it got to where I could call on the phone and say, Herb, we need a drill rig out at such and such a place. I know this is really short notice. This is has a short fuse on it. I'll give you an extra $1,000 if you could come out there Saturday or day after tomorrow. They'd always say, no problem, Dave. Save the $1,000. Just have my check there. Never had a problem. Now, when I left California, they had a going away party for me, and they invited all these different people, all my competitors. That was fun. They're telling embarrassing stories about me, and stuff. And one of the things I learned was all of these subcontractors would take my jobs and cancel somebody else out. Why? Because they knew they were going to get paid that day. You want to go first in line? You want to be the first one in line? Take your checkbook. It's very easy. Pay your bills in a timely manner. Okay. So that's not hard. That's a success principle number 2. Service is number 1. Number 2 is pay people up front. Pay people up front. They want to pay people right when they work. Spheroidal weathering is not limited to massive plutonic rocks. When I was going to Caltech, that's all I heard. You only have exfoliation in granitic rocks, plutonic rocks. And I'm sitting there going as a rock climber, and I'm going, now wait a minute. I'm down in Baja California here, the Sierra San Pedro Martir Mountains, and I'm seeing this Miocene sandstone. And you know what we called this? No, you don't want to know what we call this rock, but you can just use your imagination, the boys here. This is a nice round rock, with a thing on the end. And you're going, that's exfoliated, man. That's exfoliation, just like in a granitic rock. So I bring this back and I show it to my professor, and he says, wow, that's interesting. Well, it's not documented in the literature anywhere. That's a great out for any professor. So you bring me something, it's a photograph, and I can just say, oh, it doesn't exist because it's not in the published literature. I'm sure if it actually existed, it would be in the published literature. Folks, there's a lot of things that aren't in the published literature, like Obama's birth certificate. Spheroidal sandstone can also be concretions. You got to watch out for concretions. When you have pervious granular materials, sands, gravels, you can have groundwater flowing through those materials with carbonate that will selectively cement these materials together, and you get what's called concretions. So these are erosional remnants that formed in a young Pleistocene formation. That formation has been eroded away, leaving these cemented concretions. So those have some sort of nucleus in them, and then in an aqueous solution under a lake, they form these concretions around that nucleus. Common cementing agents are calcite, silica, dolomite, iron oxide, pyrite, and gypsum. The pyrite ones you got to really watch out for if you're putzing around with reinforced concrete, because the pyrite will go after the rebar and the concrete right now. And gypsum, of course, is another problem because gypsum is solutioned easily. Part 5, chemical and mechanical weathering that's promoted by seepage and cation exchange. Now, what I'm trying to do here with the lecture is a adjunct to what's in the book. Your book has the basic stuff you should know. So read chapter 3 in the book. What I'm trying to do is to add on to that based on my own professional experience, okay? So that's what we're doing here. So we got to start by looking at the atmospheric carbon cycle. Now, this is something that's in the literature all the time these days, and that shouldn't surprise you at all. So you should pretty much be aware of the carbon cycle. And why am I showing this to you? Because you have, in the weathering of materials, you always have a CO2 uptake when you have silicate weathering. And silicates are what by far and away, 90% of the Earth's crust, exposed crust, are silicate minerals. And so these guys are being impacted, and we have CO2 being blown into the air by volcanism. We also have sulfur oxides going up in volcanism, and we have CO2 coming out of the oceans from carbonate deposition. So the CO2 cycle is a very active one, and you really should be able to understand it. This really you don't see it much in the United States as much as if you go to Japan or to People's Republic of China, and you'll see the impacts of acid rain. It's a huge, huge issue in those places. If you go out of your hotel room in Tokyo and you grab the wrought iron balcony, what do they call that? Balustrade, it'll break. Don't sit on it. Don't lean on it. Don't have sex against it. Stay back in. Thing falls over. It's scary. Okay. Susceptibility of weathering is proportionate to chemical exchange by oxygenated groundwater. My professors never use that term, oxygenated groundwater. That's my term. I put that in there. Why? Because oxygen is the driver. The oxygen is what makes it reactive, to have oxidation reduction reaction. So it's how much dissolved oxygen, the DOC, dissolved oxygen content of the groundwater, that is going to drive its weathering ability. Now, why am I telling you that? Because the water that goes in up at the top of a mesa, if you go up and take a water sample on top of a mesa, you got some Maasai tribesmen or somebody up there, and they got their water, they're buffalo, and their buffalo are drinking. Take a sample of it. That water is going to be the lowest in cation concentration. Now go down off the mesa, come down here somewhere, find a little seep coming out of the base of the cliff, and take that water sample, and now compare the two. What are you going to find in the one down lower? Higher or lower? Higher. Total dissolved solids. Higher. Way higher. Yeah, much, much higher. So what happened on the trip down? You're having cation exchange with whatever out there. Potassium, calcium's always the number one. You're going to have calcite. But potassium, sodium, you got all kinds of things in there. So if we look at these, the least stable is halite, NaCl. Boy, that stuff goes into solution. Of course, potash is even down below that. Potash is even more soluble than sodium chloride, potassium chloride. Then you have calcite, olivine, the calcium-rich feldspars, the pyroxene and the amphiboles. These are your ferromags. And then sodium-rich feldspar, micas, potassium feldspar, muscovite, clay minerals, quartz. Quartz is less stable than aluminum hydroxides, like gibbsite. Gibbsite is aluminum ore. And hematite. Now, these guys are these things you see in the tropical areas, in the tropical soils. That's why the Viet Cong were able to make all these beautiful tunnels in these laterite soils down in the Iron Triangle, called the Cu Chi Triangle, about 30 miles west of Saigon. And we were in there. They had just thousands of miles of these tunnels they were able to cut in there, because the water table in that area is down about 27 feet, and 9 meters. And you could just carve this stuff, and the air would come into that tunnel and react with the hematite, and it would set up just like gunite, like air-blown concrete. If you ever get a chance to go to Vietnam, take the $25 ride out there and see. They have a little national park that showcases all this stuff. And it was amazing how clever their tunneling was. But the geology is what set that all up for them. They were able to do that. So here's a case where I actually did what I just talked to you about, where I actually have a little pothole up here on the top of the mesa. The rainwater and the runoff comes down here, fills up the pothole. This stuff percolates through the rock, and it's going to percolate down these fractures, and it's going to come out here where I have a little seam of clay. So I have some sort of seam of clay here. I'm going to have a different groundwater compartment above the clay and below the clay. That clay doesn't have to be very thick. Paper thin's fine. Paper thin can create a clay membrane. Clay controls everything. That's amazing stuff. And what happens is all the soluble ions along this percolation trip absorb free cations. Now, something else you don't think about, because they don't talk about this in geology class because they don't take hydrology. What happens on the trip? What's my pore pressure here?
Below
2 feet.
3 low.
What's my pore pressure down here?
5.
Yeah, could be 150 psi, depending how big this is. So when I get down here, I'm going to have more spreading outward from my joints, more pressure pushing into the country rock. So I'm going to see more weathering down in this region of higher pore pressure than I see up in here with the same batch of water. Now, what's compensating for that is by the time the water gets down here, it's more supercharged with free cations that it's picked up. So sometimes it can't absorb anymore. So it's really interesting to come in here and take little water samples right here. And what you find is the water sample is a great sampler. It's a little geologic garbage can. It tells you what are all the trace elements up there in this rock mass. Now, it's going to be very boring if it's just a pure, clean quartz arenite sandstone cemented by silica, or well, silica, you're not going to get anything. Or if it's cemented by calcite, you're just going to get calcite. And you might get a little bit of hematite and stuff if it's a red sandstone or something. But if you have a unit in here that has a lot of fine-grained materials, silts or something like that, or clays, then you're going to pick up a lot more exotic things. You're going to get some heavy metals and things like that. So really kind of interesting just to watch these kinds of systems. Here's what happens if you look at the solution cavities. These are called alveolar weathering. You get all these little pock marks. This is near Kanab, Utah, between Kanab and Mount Carmel Junction. We're in the Entrada sandstone here. And this is in Europe, they call it taphony, this kind of a thing. And this is just a cross-bedded sandstone. It's a quartz sandstone with a little bit of hematite. It's a very small amount of hematite, but it also has some feldspar in it, although nothing close to being significant. It's not going to be like 25% or anything like that. But what you have here is permeability variances that lead to these solution holes. And that's telling you that water tends to move through rock in percolation pipes. And that turns out to be the case. I studied this, and I had a long-term project in Yosemite a couple years ago, and you could really see that in some of the circumstantial evidence there where they were draining a water tank day after day after day in the same spot, and eventually you're going to get a percolation pipe going where you're going to expel all the water, all the entrapped air along that percolation path, and all of a sudden you're going to see a new spring beep out, a mile away, because all the flow is controlled by the discontinuities along that zone. But if you have a point source of moisture, it's going to tend to undo dispersion, and you're going to promote one of these percolation pipes of sorts. Here's demarcation between a sandstone strata that's been leached of its iron up here and the zone where the iron's still there. And you can see these big, large solution cavities in the iron member, the iron-rich member, but you don't see those in the one above it. And this is because of the permeability contrast that you have going here. So permeability contrasts play a very powerful role in surficial weathering up near the ground surface. Here's another one, channel potholes formed by grinding. In northern hemisphere, rolls to the right. Southern hemisphere, potholes from rolling to the left, Coriolis effect. So we got some rocks got down in here. When you get flash floods coming down here, very turbid flow, very heavy flow, this thing gets stirred up like a washing machine, and these chert or slightly harder elements will carve the pothole. And then the potholes, very commonly, this one's at a bend. The water comes down and makes a bend here and then goes this way. This kind of a pothole is a wonderful place for preserving water between storms. And you get the fairy shrimp that can actually plant their eggs in them and then go away, and a couple hundred years later, they can get rehydrated and hatch. Here's another series of channel potholes. This is at Capitol Reef National Park. And again, this whole channel is joint controlled. There's a master joint running along here, right through there. See that? That's that same joint. And then up here, the same joint. There's a master joint coming down. And this channel and these little natural bridges and things are all being promoted by the flow of water down this master joint cluster. So that standing and percolating water that you see in these pools accelerates the chemical weathering going on there. Now, if you keep this up long enough, you have up on top of the plateau here, you have potholes in the ground, and that water percolates down long enough, you can eventually get something like this. This is Double Arch, which is in the Entrada Formation at Arches National Park. And this is a very, very large structure. This guy in the blue right there is a man 6 foot high for scale. So you get an idea of the size of this thing. I was very attracted to Arches when I was between my freshman and sophomore years. I wanted to go out there and go rock climbing. We were trying to work as extras in Clint Eastwood's film Eiger Sanction, which was filming, doing some rock climbing sequences at Monument Valley and over at Zion National Park. You know, and they used some world-class climbers to do those scenes. So we didn't get in on that. But what we did do, we went off and saw everything we could find for about 6-7 weeks and just kind of bummed around between national park and national park. And that's how I fell in love with geology. Decided to become a geology major when I got back to school that fall. This is the best kind of diagram I can tell you, show you, that kind of describes, you know, deposition and diagenesis. Deposition means we got something that gets laid down, and all these things have different hydraulic conductivities. A nice cross-bedded sandstone from either foreset beds in shallow delta or from sand dunes is going to have a fairly high void ratio. The void ratio is going to be about 1 when you start. So if you have pretty much uniform sand, it's spheroidal, you're going to have an E void ratio of about 1. Now, void ratio of 1 means a lot of water can get into it and move through it quickly from a geologic point of view. So materials that are nice and clean and devoid of fines are going to have very quick diagenesis. They're going to have very fast percolation, and they're going to cement up with carbonate, typically calcium carbonate, in a very short period of time, geologically speaking. How short a period of time? A couple 100,000 years. You know, this stuff I was looking at Santa Barbara this weekend had all those beautiful joints on it. That formation was less than 200,000 years old. And nowhere in any of the literature I reviewed on the way out there, by all these, some of them by some pretty famous people, none of those geologists talked about the joints. But that's the whole problem here. The water's coming down the joints. The joints are that's what's feeding to make the blocks fall. Now, if you put something in here like a little bitty shale bed, so we had a quiescent period, we had a blockage of something somehow, and now we have some foreset beds, and we have this little shale bed here. So now we have intermediate percolation, and what you see is you can get, this is a groundwater compartment boundary. It's very important. Faults and clay seams and shale seams create aquiclues for percolation of moisture. So above this, you might have carbonate cement, and right below it, same kind of material, you can get silica cement. Now, silica cement used to make my dad's anal sphincter tighten up. Why? You're a cat driver. You're a cat skinner. You're driving a D9. You can rip anything with carbonate. Piece of cake. It's actually fun. As soon as you get into silica cement, it's going to rip you a new behind. Why? The silica has a hardness of 7. Calcite has a hardness of 3. What's the steel on the cat ripper blade? 5.7. Hardened A36 or A100 steel. It still ain't anywhere near quartz. So what that means is you're going to go in there and have a lot of abrasion. You're going to have guys tack welding on there 3-4 times a day. And you're going to burn up a lot of arc welding. Today we have these powdered metals they can spray on. Powdered metals, oh, so neat. It's like spraying on, airplane paint, on your model airplane. Except they cost $300 a little can. And you go, ooh, I could pay a lot of kids to do a lot of arc welding beading for $300. Yeah, so it's more expensive, but it is a lot easier to use. But different groundwater compartment now between here and here. Completely different chemistry because that little seam. Now, we go down to bottom set beds. Bottom set beds is your fine grained material, siltstone. Going to have a little bit of clay in it, but it's mostly siltstone. Siltstone has very low permeability, so it takes a long time to percolate water through it. Now, the longer it takes to percolate water through it, the longer it's going to take to undergo diagenesis. Diagenesis is a petroleum engineering term, petroleum geology term for lithification to rock. So how we go from being a soft sediment to a nice, friendly, hard bedrock, that's diagenesis. And diagenesis, of course, what happens on this trip controls whether you have oil or gas there. I mean, if things get hot, what happens to the gas? Gone. You don't find gas fields near volcanoes, for instance. It just doesn't happen because the Earth's crust temperature is too hot to have gas retained. The gas is all blown out and is gone. So diagenesis, a lot of attention is paid to diagenesis because that's the crucial factor in coming up with the depositional models for where we're going to find fossil fuels. So we look at diagenesis, they look at thin sections. They look at how something changes with time by looking at thin sections. Now, I wasn't a big fan of thin sections in college because in those days they made us make them by hand. And they were a super pain in the butt. You sit there and you're sanding this little thing. You're trying to get it down to 1,000th of a millimeter or something, and you're sanding it, and I'd look at it, and just not quite where it needs to be, and I put it on one more time, and then I come back, it's gone. I just lost an hour and a half. So I didn't like thin sections because they're a pain to make. But if you get somebody who knows how to do them all the time, pay them $10 to make your slides for you, there's a lot of things you can learn from them. And later on, when I was about mid-career, I learned that I run thin sections on everything, just as a matter of to see if I'm missing anything on a microscopic scale, especially nasty things like pyrite, that you're just not going to see with your naked eye. But anyway, what happens here, this takes millions and millions and millions of years to go through diagenesis because it's such low permeability. Now that makes sense. So what that means is by the time this thing becomes rock, you have a whole lot more load on you. Might be 10, 20 million years instead of 10 or 20,000 years. And so by the time you get over here and you lithify, this is much denser. So if you look at the unit weight of a siltstone, typically I would get 135, 136, 137 pounds per cubic foot, up to 150. 150 is concrete. What did I get with the sandstone? Massive sandstones, fun to do rock climbing on. 116, 120. Nowhere near as heavy, unit-wise, as the siltstone. Well, that's because the siltstone took so much longer to get sedimented. It had significant consolidation by the time it gets lithified to rock. So you got to think this way. I'm looking at the diagenesis process as a function of unit permeability. And I have to look at weathering as a function of what? Unit permeability for the area you're at, the geomorphic setting. So you're near the base of the cliff, you're going to have what? Higher pore pressures, more infiltration, more chemical reaction. More surface area has chemical reaction. In the area that has low pore pressure, you're just traveling down the joints. You're not penetrating side to side nearly as much. Okay, here's an erosional escarpment at Bryce Canyon National Park, where I went to ranger school the summer after I decided I wanted to be a geology major. And here we're actually seeing limestone and marl spires, and these are forming in big, long rows between regional systematic joints. So these things are all parallel to each other along these joints in the tertiary, it's Eocene age tropic formation. And these are marls, these are lake sediments on the land, carbonates. So here's what it looks like when you're down the bottom and you look up, you see all these spires. And for Ebenezer Bryce, it was a heck of a place to lose one of his sheep. He was this Mormon shepherd, down there, and you get a sheep up in here, you'd never find them. You could hear the sheep bleeding, but you couldn't find which of these things he had wandered up. And so these are all percolation corridors where lots and lots of water is coming down. And the Terra Rosa, the red here, is the weathering of the carbonate marls. Now, when you fly along in a helicopter, this is the view you get. You're flying along the escarpment. This is the Park Service campground back here, and you're going, whoa, look at these things. Big, huge openings. What are these? These are percolation conduits along those master joint sets. So we come back in. There's a joint set down there. There's one right here and here. Parallel ones over here. And this one, this is about 100 feet across. That's a big arch. You can see, I wouldn't want to build, the hamburger shack right here or something, or put a parking lot right there, because that's going to drop down here. But very, very impressive amount of percolation going on. Now, what's driving this is the excavation of the escarpment. So this groundwater table over here, and this whole area is being pulled in this direction towards this escarpment. And this is up at fairly high altitude. You're a little under 9,000 feet. So if you're going to go to Bryce Canyon, they've had a heavy snow that year. You're not going to get in there till July. It's very, very high. Now, this is over at Arches National Park, and we're looking at here are sandstone fins that were formed in tension because over here to the left, in this direction, we had something called the Salt Creek Anticline. And the Salt Creek Anticline pushed everything up. This big salt dome came up, and this sandstone on the flanks was split up into tensile fins, and it's in these thin tensile fins that you get the natural rock arches. So there's what one of these fins looks like. It looks like the prow of an old battleship, like the Arizona coming up, and they're thin, and they're very, very long and continuous, so they have plane strain conditions in the direction of the fin. And there's a lot of residual stresses locked up in these things because they were buried during the Jurassic age. And so very, very old material going back to around 85 to 100 million years ago. Very low tensile strength. So if we get inside of an arch and we look here, and I was a rock climber, first came here in 73 when we were up there trying to be in the Clint Eastwood movie. And I got in here and I saw, man, look at these exfoliation joints. You can't even count them. There's just so many of them right in the center of the arch. And then right here is a bedding contact. And they stop. You see one or two right here, but they just stop. And I go, why do they stop right here? And I took a sample. You're not supposed to do this, by the way. I looked at the rock over here. I looked at this rock over here. They look like the same rock. But their properties are different. So I went to Berkeley for grad school after the Marine Corps, and I said, this is what I want to study. And they just shook their heads, and they said, talk to Fred Donath back at Illinois, or talk to this person. I talked to all these different famous people. And Donath was actually the biggest help. He was a structural geologist. And he said, it's stiffness, Dave. This is brittle material, and it has a different stiffness than this material. If you did enough tests on these things and looked at the stiffness and the tensile strength, you're going to see a big difference between. And that turned out to be prophetic. That was exactly true. Okay, so we're finished with part one, or the first half. Let's go on to the second half here. Let's see. There's my removable disc. We're going to go on to weathering parts 6 to 11 now. Got 45 more minutes. Any questions up to this point? You should have questions. That's the bad sign. No questions? All right. Wow. Means you haven't done anything yet. Weathering of carbonate rock. Well, carbonate rock is a big issue all over the world, especially in Asia. You really want to see karst topography, you got to go to China. And they have it on a spectacular scale. China is like a giant California. California has this very diverse, tectonically active margin, incredible geology. I mean, you can go see glaciation features one day, deserts another day, and beaches on the next day. And they're all right there near each other. China's like that, but on a tenfold scale. Just wild geology. The great geoengineering challenges are going to be in China over the next 100 years, believe me. And so if we go to California, not a lot of limestone in California. This is the only one I can think of is Lake Shasta. We got this big mound. And when limestone weathers under subaerial weathering in a subhumid, subarid climate, you see this bluish color tinge to it. And you can see here just a lot of exposed rock. In fact, Shasta Caverns is right there. And that is a material that from an engineering point of view can give us a lot of heartache, and does in the Ozarks, because of the carbonic acid from rainwater and rain percolating through decayed forest litter is going to weather those feldspars and calcites. I showed you that earlier. And so if we actually go out on a weathered surface and look at carbonate, again here we see all these joints, and the joints have water percolating down them, and the joints are all filled here with soil. And so in the Midwest, rainwater can dissolve 1 millimeter of limestone every 25 years, where you have an average precipitation of 34 inches a year. That was Winkler's work at Notre Dame. And the reason I put down 34 inches a year, that's the average rainfall in South Bend, Indiana. Okay, so you can't take his number and use it someplace else. That rate's actually higher if you go down to someplace like Memphis or Jackson, Mississippi. It's even higher. So as you get more tropical, subtropical, you're going to have more weathering of carbonate. Now, how did they do that? They went out and measured headstones. And those are all pretty recent, geologically speaking. I mean, headstones in South Bend aren't much past, they're nothing past 200 years, I wouldn't think. So that area just got settled after the War of 1812. So here's a terra rosa. That's a type of residual soil that forms over limestone. It's typical of subhumid areas, and you get this reddish-brown soil that starts infilling the joints. So this is an old quarry. This is one of those old rock quarries, and tree roots often follow those joint lines down, and tree roots cause mechanical weathering. One time we had a big rock slide. It wasn't a big rock slide. It was a modest rock slide up at Yosemite National Park. It came down right in a zone where they do a lot of rock climbing. So we went out there, with our binoculars, to look at this thing. And we see this big black line coming down. It was way too big to be a climbing rope. Turned out to be a root of a ponderosa pine tree. And that root went down 350 feet. And all the tree people said, not possible, not possible, not possible. Well, you got to go out and look at it, I mean, that's what it did. And so that tree root went down there, and that tree root's growing every year. And so it's expanding the joint out further and further. And finally, one day, the joint block fell away under direct tension. So this thing just broke under its own dead weight and buckled, and down it went. And there was the tree root exposed. Now, this is called rillencairn. Rillencairn are small solution pockets a few centimeters apart that are separated by these sharp inner grooves. And this has nice high friction. If you're a rock climber, you love rillencairn because if it's not too slimy, it hasn't been raining, it had water running over it, you get good friction on this kind of material. And you try to keep 3 points on the rock at all times. 2 feet in one hand or 2 hands and 1 foot. And you only move one thing at a time when you're rock climbing. So you get solutioning in these little pockets because you have slightly acidic rainfall that sits in here. It solutions a little bit of the calcite, and then it evaporates away or gets blown away in the next storm, and you get this kind of an erosion surface. And this is our nemesis, Osama bin Laden, and he was giving an interview in somewhere in Afghanistan. You can actually see this is Rilin Karen right behind him here. This is in the Tora Bora Mountains somewhere. Anyway, he doesn't do that anymore. He always has a big bed sheet behind him now, so we don't get to see the geology or the interesting places that he's staying at. So this is flying over karst on the north rim of the Grand Canyon. This is karst that's developed in the Permian age Kaibab limestone. And it looks like bomb craters. You see all these little closed depressions, kind of like flying over the area down here near Kabul to West Plains. That's pretty typical. You have an underground cave network, and so all this rain comes down on the Kaibab Plateau because it's so high. It's 9,000 feet high. And for years, nobody could figure out where all that water goes. Well, it goes into an extensive underground drainage system. And when you'd fly over the Kaibab, you'd see things like this. Big, huge sinkhole here. And then newer, smaller sinkholes. There's a fresh one right there, about 30 feet in diameter. So you get an idea. If that's 30 feet in diameter, this is a big guy right here. It's a real, very large sinkhole. But all over the Ozarks, we see these same kinds of features. In fact, if you look at a LiDAR image of, I'll show you one of North St. Louis later, it's startling what that area looks like in the St. Louis limestone. Here we're actually over Auburndale, Florida, flying over it, and we can actually see an arcuate crack going across the asphalt, and some more arcuate cracks, and more arcuate cracks, and you come around over here and you see the suggestion of another one right here. That's precursory dropping of a sinkhole that's going to form right in this area. And at this time, the sinkhole was about 2 feet deep. Now, of course, when you start sinking like this, these things are all over Arizona, along the Central Valley, or the Central Arizona Project, and the Palo Verde Canal that comes over from the Colorado River. When you get these kinds of things forming and they start getting 2 feet deep, now all the runoff and the rain that comes down these things, especially if you have a canal crossing it, it's all going to feed into this thing and accelerate the formation of the sinkhole. Here's another one where you got a USGS geologist standing in one of these newly formed tension cracks bordering one of these sink features. So that's just a matter of time where the thing's going to go. And there's what it looks like when it did. This is one at Winter Park, Florida. It's in all the general geology textbooks. It's about 200 meters in diameter or so, and 100 feet deep, and 320 feet wide. So it's about 110 meters, something like that, 100 meters wide. And this thing just dropped down, and boom, you got a major engineering problem. So that's the problem with karst environments. Here's what it looked like on the ground. Give you an idea. This is a camper for scale that's gone in. This is a big tree that's going down the middle part of it. You can see some of the buildings that went into it. Obviously, you get something at that level, and you can't even let the people go in to get the stuff out of their house or anything. It's pretty frightening.
Was
Yes?
that the Ferrari dealership?
No, I don't know if it was or not. I can't remember now. There's a lot of stuff on the internet about this particular one. It's probably it's one of the highest visibility ones we've had. Now, this is actually around here. This is Slaughter Sink, which is over here real close to where they did the relocation for westbound 24 when they built the second bridge over the Little Piney. So this is just out west of town here, 6-7 miles. And this is one of the largest sinkholes in the Central Ozarks. It's called Slaughter Sink. And this one's actually filled with water. That's the water table in this area. So you'd want to note things like that and get an idea. And there's a lot of these filled sinks all over the Ozarks that were mined in the old days for iron. That's what the Merrimack Iron Works were. They were old filled sinks that had iron-rich clays in them. They were mining those. If we look at how most limestone caverns form, they tend to be influenced by jointing and bedding. So you have bedding going down this way. You got jointing cutting against it. So you have these arms of a cavern, and in this case, the caverns underwater, or the caverns coming up right near the ground surface, and you have a little bit arching going across the ground surface and it hasn't broke in yet. And these kinds of features are going to be influenced by the regional groundwater table. So solution chambers can lie around a considerable depth. If they're below the groundwater table, they're filled with an acid-charged water. And they're not going to do anything. The water carries the load because water is incompressible. It's got Poisson ratio of 0.5. But then if you excavate a canyon or something over here, now that's going to change the regional groundwater table. And this thing's going to start to exert some influence. And typically when you get inside these things, what you see is you'll have blocks that have argillic coatings and have clay and detritus that's fallen down from the roof. And then down here, you'll have speleothems and other things that are growing actually on these blocks because these blocks are underwater. So you can actually date these much easier than you can date these guys. But you can have partial collapses are very, very common, especially when the water table goes down. Water table goes down because this canyon has been cut over here. That's brought the regional water table down. Then you're going to get all these blocks starting to fall in because you've increased the effective stress, the weight of those blocks. So what happens, the cavern, you have continued solutioning, the cavern actually starts filling up and it deposits speleothems and calcite on the blocks, and then other blocks in here are completely buried in residual clay that fill the interstices of the cavern floor. So now the speleothems are going to be up here, and these are going to be buried in the clay material. There's a real interesting one, looks like this, underneath the northeastern side, the Muslim quarter of Old Jerusalem, that colloquially called Solomon's Mines. It had nothing to do with Solomon. It was far post-date Solomon, but it's back to the Herodian period, 1st century BC, and afterwards. And you see a lot of these same kinds of features. And there's a big underground quarry that was used to quarry the blocks to build the Temple Mount in Jerusalem during the period of Herod's reign. And so here we see during wetter climes, now you're going to fill up with water, depending where the regional groundwater table is. And the calcite-rich groundwater is going to deposit speleothems on these blocks, and it's going to wash out some of the residual clay. Well, that's the problem. This residual clay, let's say I come in here now, and somebody wants to build a dam in here. So I'm going to come in here and drill holes and try to inject grout under pressure anywhere there's a gap. Well, the clay is not going to let the grout in. Clay is plastic. So then you go, okay, the ground's taken as much grout as it can take, and I've done it under, 100 psi injection. And now you build the dam, and you put a couple 100 feet of water on it. Well, that water pressure is going to push some of that clay out. And 10, 20 years, 30 years later, your dam starts leaking. And you call the grout contractor back, and he grouts again, and you just keep repeating the process. So one of the things you learn about if you have a karst area like Missouri, southern Missouri, and Illinois, Kentucky, Tennessee, become a grout contractor. You're always going to have work. So now, drier Holocene climate, this is kind of the cycle we're in today. Now you're going to have adjacent downcutting down here. You have less rainfall in this latitude, 38 degrees north latitude. We got about 40% less rainfall than we had between 100,000 and 14,000 years ago. And so we're going to have a drawdown of the regional water table, drains the caverns. Now we're going to deposit more speleothems on these rock surfaces. That's what all these little sharp things are. These are little speleothems. And those are things you actually can date, the ages of them. This has been done in all the caverns around Grand Canyon to unravel the evolution of Grand Canyon. And it turns out that one of the theories was right. It eroded over the last 4 million years from the west to the east. No question about it. They got a real clear record of that in the speleothems in the caverns developed in the different limestone units as you go down. And so here you can see most of these caverns get filled with fall-in block debris and clay. So these become very, very problematic if you're trying to build reservoirs, like the Merrimack project over here, which is covered on my website if you want to read about it. Big, huge dam they came in to build, got all the federal appropriation, got all the money, went in there, and when they started to build the dam, they found a cavern 300 feet long and 70 feet wide in the right abutment of the dam. How the heck did they miss that? Easy. They weren't looking for it. They weren't looking for anything that big. So you won't generally find things you aren't looking for. You got to be looking for something. All right. Chemical weathering promoted by precipitation of salts. Nobody else talks about this subject. I got onto this working with Egyptian antiquities, where we have big problems with salt attack for a variety of reasons. And it's everywhere. If you start looking around the planet, you'll see these kinds of issues just about anywhere you go in a sub-arid to arid environment. So and this is the kind of things we have in Las Vegas, Palm Springs, Phoenix, any of the drier areas. You have to really understand your salts and what your families of salts are. Now lichens, this is down in the Ouachita Mountains, down in the Arkansas. When you walk around the Ouachita Mountains, now you're in an area that's very humid, and we have this granite core of the mountains, and the granite is seeping all this moisture, and we got all these exotic lichens growing all over the place, which is great if you're a downed pilot trying to escape and you want to eat scrambled eggs every day, right? It's a wonderful smorgasbord for you. But these lichens secrete very, very acidic enzymes which attack the feldspars. They attack the rock, and so they live off the rock. And if you look up close, these are lichens and sponge moss growing on a sandstone unit. These will actually give you a pitted texture. If you scrape all these things off, scrape them off, you'll find a very, very pitted structure. Goes after the ferromagnesians and the micas first, and then the feldspars. Here we are in the bottom of the Grand Canyon, and I'm actually in the Vishnu schist, which is a 1.8 billion year old crystalline rock, and we're looking at foliation plains here, and we got salts, sodium chloride and potassium chloride. This is actually Epsom salt. This is that stuff that I told my class about. If you drink this stuff, you actually get diarrhea, and I learned the hard way about that. And Epsom salts are pretty common in the desert, so you got to be careful whose well you drink out of. So if you read T.E. Lawrence's book, 7 Pillars of Wisdom, about his experiences down in Arabia and stuff in the early World War I time frame, what you learn is, these different Arab clans would shoot people. If you weren't in their clan, you were taking a drink out of their well, they'd shoot you and kill you, and then ask questions later, because the wells that had potable water were very few and far between, and your livelihood depended on those wells. And what was one of the chronic problems? What did your enemy do to the wells?
Salt the well.
Yeah, they pollute them. They didn't salt them. They put poison in them. If they put poison in it, you couldn't call up the environmental cleanup contractor. They just weren't in the yellow pages yet. And so they would shoot somebody and kill them first and ask questions later. And it's hard for a Westerner to understand that unless you live in the desert for a while. And you realize, well, water and the water quality is life itself in the desert. It's not funny. It's serious stuff. And in L.A., if you go to Southern California, water is what makes land valuable. Land, you want to buy cheap land, go to Grand Canyon. Take a trip to Grand Canyon, I-40, turn off. You'll see signs everywhere. 40-acre ranch for only $40,000. And if you're from Missouri, you're going, whoa, that's not a lot of money. I could actually be a land baron. Yeah, you can. How far do you have to drill for water? Well, in Rolla, you have to drill about 100 feet, 90 feet maybe. In Arizona, you have to drill about 6,000 or 7,000 feet for water. How much do you think the well is going to cost? A lot more than your ranch costs. That's how much. Yeah. You can't get water in northern Arizona to wash off your windshield on your car, even if you fill up. You can go in and buy some Dasani and use that on your windshield, but they're not going to give you any, because the water is expensive, and the value of the land goes with it. What this is water from this creek, Clear Creek. The waters come up, the water cycled down in a storm, and as the water gets evaporated out of the bank, even in the seemingly tight schist, the salt is precipitated. Now, if I put a reinforced concrete structure here, that salt's going to go after my rebar real fast. So when we're doing rebar in the desert or next to Pearl Harbor, anywhere where we have salt water, you better be using tight cement mix, water-cement ratio less than 0.45, is what I was telling the guys in Santa Barbara this weekend, and you better use epoxy-coated rebar because you're going to get salt attack. No question about it. You go out and look at all the bases that we built out in the Pacific in World War II, all of those structures where we use reinforced concrete have suffered grievously with salt attack. Most of them aren't there anymore. They're gone. Here we are in the Gulf of Thailand, and what I'm actually looking at here is a granite outcrop. And what's all this white stuff down here? Well, this is sodium chloride, salt spray from the ocean, from storms that come in here. When you're in the Gulf of Thailand between mid-May and mid-October, it rains every day. It isn't a question of is it going to rain today, it's how much is it going to rain today, and am I still going to be here at the end of the day? Because they can get, one day I was there at Pattaya and we had 17 inches of rain, 17.56 in 24 hours. That's a lot of rain. Yeah, I didn't have to turn my shower on that day. It just came down in buckets. So now, when it rains real hard, a lot of this salt will be washed away. Then this salt will show back up as you have storms come along and you have salt spray onto the rock, and it will affect things that have low tensile strength, high permeability, like sandstone. All right. Last one I want to mention, or the last one on that kind of track I want to talk about is precipitation of travertine. This is actually me right there when I was barely 24 years old, and I was leading a research trip down the Grand Canyon of the Colorado River. And here we've made a left turn, and we're in the bottom of the mouth of the Little Colorado River. And the Little Colorado River has some big springs about 3.5 miles upstream, and those springs are very, very high in calcium carbonate. So this turquoise color you see here is the calcium carbonate. And it's very high solubility, and the water temperature is about 70 degrees. So it's very nice, warm water. Now, as soon as the first thunderstorm occurs in July, around July 4th or so, this will just turn into a red mud pond. Little Colorado River has the highest silt load any river in the world. In the world. 70% in trained solids coming out of that river during storms. That means if you scooped up a quart size, tomato paste, about 70% of it would be silt and rocks and stuff. That's a very, very high. And that's because of dispersion, having dispersive clays in the formation. Those clays don't come out of dispersion. They create a very heavy mass as if the debris flow coming down that channel, basically. So travertine is very commonly deposited in arid areas. Basically, it's dissolved in the groundwater as it percolates through carbonate formations, but even it carries that carbonate as it goes through non-carbonate formations, and it will actually precipitate out down here in the warm water zone in the upper 30 feet of some body of water. So if you have a body of water here, and it'll give off CO2 when the carbonate is precipitated. So what do we have going on there? We have carbon dioxide dissolved in groundwater, percolating through the limestone, forming a weak carbonic acid. That reacts with the limestone to form a soluble calcium carbonate, which is this CaH2CO3. When that mixture spills over small falls, it's aerated. So if you have a place here where it hits something that's resistant and it spills over that, it aerates it, and you get dissolved carbon dioxide into the dry atmosphere, and you get insoluble carbonate and water given off. And I'll show you what that looks like. Here's one, Lake Cahuilla, sometimes called Blake Sea. This was discovered back in 18 56 by a guy named Blake, who was a geologist with a U.S. railroad survey. This is down in what's now Imperial Valley. And you can see here, this is an old lake surface right here. When you climb up here and look at it, this is all travertine. This dark gray stuff is travertine. And there was a lake that was sitting here, a freshwater lake between 700 and 1700 AD that's about 20 times the size of the current Salton Sea that's there today. Here's the carbonate bathtub ring that I took pictures of as a teenager out at Lake Mead. So I'm standing at Hoover Dam. I'm looking back upstream and Black Canyon. This is Fortification Hill right here. And this is from the high water mark that was only 3 months long, August to October of 1941. So they drew it up here. They tested the spillways. The spillways had cavitation problems. Then they drew it back down to their design flood storage. That's when this picture was taken. And not too long after this picture was taken, 1964, 65 time frame, they ended up bringing this back up to about here because they had Glen Canyon Dam upstream to help them with their flood control, flood storage issue. They reduced the flood storage from 9.5 million acre feet down to about 1.8. So right here, this was deposited in 3 months. That whole bathtub ring you see miles away, 3 months in an arid environment. So it doesn't take long for travertine to be deposited. Here's Lake Powell, picture taken in Lake Powell, 2005, when Lake Powell had drawn down about 90 feet. And again, this is red Navajo sandstone. This bleach line here is from the 1983 flood. So that began filling in 1963. It did not fill completely till 1983. It's supposed to fill a lot faster, but it took 20 years to fill. And then now it's at a record low. It's actually down around 147 below spill right now. So what's going on? They did a lot of studies at Lake Powell because they were worried, like Aswan, like Lake Nasser on the Nile, they were worried about how much water are we going to lose to three things. Now, when they first filled Lake Nasser, it was an eco-disaster. They lost 1/3 of the water to direct evaporation. Big, huge lake. You look at Lake Mead. Lake Mead is behind Hoover Dam. Hoover Dam's like, really, really narrow. There's more concrete than actually in Glen Canyon. But Lake Aswan Dam is long, big, long dam. So you have a very different ratio between depth to volume, or area, exposed area to volume of water. So they lost 1/3 of the water coming in to evaporation. They then lost another 1/3 to percolation into the Nubian sandstone. And then they lost the last 1/3 to watercress. They didn't go after the watercress, and they lost it in evapotranspiration, which surprised everybody, not just the Russians and the Egyptians. Everybody was surprised. America had always had a real hard line on arresting watercress so we wouldn't have the evapotranspiration loss. And the Egyptians became masters of that craft. It didn't take them long to realize we got to get the watercress under control here. We're not going to get any money out of this project. It was an economic disaster. Well, what happened with the Nubian sandstone, over the first 6 years, the Nubian sandstone stabilized. So it took in all this water, but each year it took less and less and less to where it reached a stabilization point. So these studies of these big lakes and desert areas, one of the things we've learned in these lake studies at Lake Powell was that travertine deposition was stimulated by the presence of algae in the warmer lake water within 30 feet of the lake surface. So it's in this area, in the photosynthetic zone, where we actually get the travertine deposition occurring. We don't get it deeper in the lake. And that doesn't matter whether we're in sandstone or limestone or shale. So that's an interesting finding. The other thing we learned is that diatoms in the water also stimulated carbonate deposition. So when we have a deep lake, we actually get cyclothermic currents that occur, especially seasonally. And the diatom formation is going to be up here in the photosynthetic zone. It's going to be in the upper 30 feet. And in that zone is where we tend to foster the carbonate deposition very, very rapidly. So you can see here, this becomes a big issue, like for my client this weekend. He has a swimming pool out there. It's a $40 million estate. and they got the swimming pool right out there, right on the top of the cliff, and of course they had waterfalls on it, and what do they got? They got all this white stuff all over the place. What is this white goop, Rogers? Can't we get rid of this white stuff? You know, it's carbonate. And the problem is, he's right out there on the bluffs, and the bluffs are 200 feet high, and they're on a point of land, which makes the view better. But if you go over here, there's no point of land. You go over there, no point of land. It's a fault that creates that. But it's a big fault drag fold that lifts that point up. Well, when you get something like that, you're going to get thermodynamic flow. You got this ocean coming along, and the wind's going to come up. It's going to be windy there all the time. And they said, you're exactly right. We don't even use the pool anymore because every time we go out there, we get cold. It's so windy. And I said, well, the wind blowing by is causing the evaporation, and that's why you're going to get all that carbonate. Like, you have to put a softener plant in here and soften the water, take all the carbonate out of it, and that'll take care of your problem. And you have to go to acid bath to get rid of the carbonate that's there. But I said, everything that's got arteriolosclerosis. It's going to plug up here before very long. You can just see all this carbonate. So, kind of interesting. I don't know, what else did we learn here? Diatoms are in the warmer surface waters. They stimulate carbonate deposition, and that lake salinity increased with depth. Well, that shouldn't surprise any of us. You should expect the salinity to increase with depth because of gravity. This is going to be heavier fluid. It's under more confinement, and you're going to tend to get higher concentrations of TDS down sitting here, whereas up in here is the activity zone and the fluctuation zone. And you're losing some of the salt to the precipitation. All right, so what were the conclusions of the Lake Powell studies? Salinity increases with depth, temperature decreases with depth, but then increases right near the bottom because of density currents. That was discovered on Lake Mead in the 1940s, how density currents work. They actually flow 116 miles through very tortuous canyons on zero gradient all the way to the dam face, heated up the back of the dam, and they had a big problem with getting too much warmth at the base of the back of the dam. How much is too much warmth? 70 degrees. What's the normal temperature, the water down there at 500 feet? 37.4. That's a big difference. Dissolved oxygen content is replenished at depth during winter months due to cyclothems. So heavier, colder water is heavier, so it tends to be subducted downward. Silica is extracted from the lake water by the diatoms, and we use that now in trying to plug up leaky dams. We have a dam in this kind of situation. One of the things, I worked on Glen Canyon for my doctorate, so that's why you're hearing so much about Glen Canyon. But one of the things we had there, we noticed, is as the lake came up, we had about 5,700 gallons per minute just flowing through our grout curtain on either abutment. We couldn't do anything about it. The sandstone's so fine-grained, we couldn't get the grout penetration. They did all kinds of grout studies when they built it. And so I put all these rock bolts in and all these drains. So we're monitoring all this water coming around each abutment, and we're worrying because as this lake's filling up, what's going to happen with the pressure head? Pressure head's going up. So we should get more water. The opposite happened. We got less water with time. The reason? Carbonate, travertine deposition. So you can help yourself out here. If you have this, you're building a dam in a semi-arid area, you can bring out a nice scow, a floating barge, and get a lot of carbonate on either abutment and let it percolate in and help you out. Photosynthesis in the surface waters produces high pH conditions which tend to favor precipitation of calcite. It's got reverse solubility. And calcite precipitation appears to be controlled by the pH, the temperature, and the surface area of the calcite nuclei. So it's really very quite interesting. These issues have really come home to roost now. I've been getting calls from places like Saudi Arabia where they have dams and they build them with Western designs, and they're finding that all their instrumentation is fouling. And that's because they're getting exotic sulfate salts as well as sodic salts and potassic salts. And I laughed when they sent me the pictures of these things with all this goop coming out of the in the galleries. And I said, well, you realize Hoover Dam and Glen Canyon, we don't have any instrumentation in those dams that works today. All the instrumentation's been fouled by salt precipitation. And we're just going along hoping we don't need it. It's going to come home to roost on us sooner or later. I don't know. All right, here's Marble Canyon, which is the upper Grand Canyon. It's deeply incised into this thing called the Marble Platform. This is the Kaibab limestone. So this thing gets deeper and deeper and deeper as we head toward the Grand Canyon. I'm going to take you down there now. This is my first trip down there. I've done 7 trips down the Grand Canyon. This is my first morning at my campsite at House Rock, mile 17. And I'm looking down canyon, and I see these guys. See those white, it's like somebody painted white lines on the Toroweap Formation, way up here. That's kind of interesting. So I got curious about that. And what I later learned, the next year, I developed this whole model, which has been verified now by work by the U.S. Geological Survey. There were a series of very large lava dams and landslide dams in the Grand Canyon in the late Pleistocene that backed water up to as much as the 4,125-foot level right here, where I show it here. And these are the bathtub lines up here, the carbonate deposition from these fillings of these lakes. So this is down where the lava dams actually occurred, down around river mile 179. So we're 179 minus 17, you know, you're about 160 miles, 62 miles downstream. There's a series of volcanoes where these materials came down, 3,000 feet down, formed these lava dams, one over another, and they would back up these temporary lakes. And when you looked at the travertine deposition in the central part of the canyon, it wasn't tied to the geology. Everybody assumed it was. They said, oh, we get travertine. You get that in waterfalls and springs on limestone. But when you went in here and actually looked, you had travertine on all the formations, just draping like, looked like shotcrete. Somebody come in there and just sprayed this shotcrete on. This one was extensive, 1,300 feet high of just travertine over shale, over limestone, over sandstone, over marl. So I started to correlate all those through the canyon. So here we are in the upper part of the canyon, around mile 56. See right here? Mile 56. And now we're going to go 100 miles out to the west, down here. And what I'm doing here is I'm tracing where all the travertine deposits are and the gravel deposits that are anomalous. And what you started seeing was these things correlated over long distances and suggested they correlated with water levels. Because you can see here, the maximum high water stand is just constant all the way across this thing, all the way over to here, regardless of where the bottom of the channel is. That was kind of interesting. And so I did a frequency analysis, and pretty soon by doing a frequency analysis saying, okay, at these elevations between here and here and here, and these are groups, how many deposits? And you see we had 8 deposits that peaked out at that same elevation. We had 8 deposits that peaked out at this elevation. And these are the elevation groupings, 2350 to 2480 and the 3320 to 3480. And it turned out that's where these major, the level of these major landslide dam and lava dam impoundments were. And so if we actually look at that, the highest one was called Prospect Lake, and it would have backed water up several hundred miles from mile 179 here. This would have gone all the way up, well into Utah, and all the way up to the Colorado line. So these were there. That was the largest one of all of them. Very, very large impoundments. And if we actually look at the detail of it within Grand Canyon itself, we can actually see that this lake had a depth of about 1,500 feet. And there's different places where I've looked at it. There's River Mile 57, River Mile 116, and 157, where they have these very extensive travertine deposits all at the same level. And this is where the lava dam was, way out here. So this is some really fun work that I came about as an adjunct to my work at Glen Canyon up here. Since I was here in Glen Canyon, I started going down here and exploring the Grand Canyon. It became my lifelong hobby. So, erosion by water and wind. This is an aerial oblique view of Badlands in South Dakota. This is the Pier Shale. It looks like Pierre Shale. Don't pronounce it that way. It's pronounced Pier. It's kind of like in the Ozarks. We got Walmarts. Doesn't have an S on the end, but that's a possessive. That means that's my Walmart. Walmarts. And so note complete absence of any stabilizing vegetation. Now, if you're a geotechnical engineer and your client's area looks like this is good for one thing. And that's called sediment studies. I mean, there's nothing growing there. That should scare you. So let's get over to the eastern edge of it. So I'm flying along now. I'm at the eastern edge. And now I can see I got some semi-stabilized platforms down here. They got this fescue grass growing on them. And I got all this other stuff that's just slimy and coming unglued and yucky. Well, you'll find out what it is real fast when you get on the ground. Get boots on the ground. Go look at it. And I went out and I looked at it. And I was being real careful because it looked, and I fell right on my butt. Now, that's the fall on the butt test. FOBT, fall on the butt test. And that tells you what? Can anybody guess? Smectite clays. Yeah, it's montmorillonite. That's the Bear Paw Shale that creates that problem. So Pier Shale, the Bear Paw Shale, all have montmorillonite in them from altered volcanic ash. So this stuff, the reason it's just eroding like crazy like this is it's got smectite clays in it. So you can't stabilize it very easily. Here's what it looks like on the ground. So you get on the ground, you look at it, and on a dry day, you can go up and take a picture like this. If it had been raining, you can't even get up here to take that picture. You just slide on your butt. It's just really wicked stuff. But it makes for a good national park. So here's another one that I found out near Pioche, Nevada. Southeastern Nevada Nevada's got some really pretty places. They just don't put highways through the pretty places. This is a state park, Pioche. It's a wonderful place to go at winter break. And these are lacustrine or lake sediments. These are Pleistocene lake, huge Pleistocene lakes out there during the late ice ages. And these, again, have been all eroded away by the upper Muddy Creek, which flows down into Lake Mead. And this, again, is high montmorillonite content. It's got a lot of smectite clays. They swell up to about, 300 to 800% of their dry weight. The calcic swells less. Calcium montmorillonite swells about 300. Sodic montmorillonite, stuff we use in drilling mud, swells up to 800%. So it's really loves to absorb moisture. And so if you look at a block diagram, this is illustrating the quantitative relationship between runoff velocity and stages of erosion. You see you get rill erosion up in here, and as the rills join together, you get greater stream power, then you start getting gully erosion. So gully erosion is a matter of getting enough stream power and enough velocity to downcut, and then down here, you'll cut these gullies, and then you'll start getting deposition because of the hydraulic jump that occurs down here toward the bottom. So where this bottom line is changes the profile dramatically. This is the velocity profile here showing you. So where my profile velocity is very high, I'm going to be cutting down through this stuff. This is a big issue when you get out on construction projects and you're supposed to be abating all the erosion. You've got to start thinking about stuff like this and saying, do I have material that is really erodible here? Well, that's a huge issue if you're operating in an area that has large storms. If you're operating in the tropics, you're operating in humid areas where you get high levels of rain. So what do? You have to try and limit the runoff velocity versus the erodibility. And you got to realize, this is a Corps of Engineers chart, that you're using silty water is what you better be designing for. We always have clear water stuff here because we can calculate those very easily. There is no such thing as clear water flowing out on the ground surface when it's raining hard. I've never seen clear water. Clear water is only in civil engineering hydraulics labs. They got distilled water there and they do everything with that, But when you get out in the real world, it's going to be turbid water, and you're going to have to be designing for these kinds of numbers. And you got to realize if you put it on something that's really steep, you're going to have highly unsteady edified flow. And that really becomes problematic because then if you have something that's a hard point, like a rock here or there, it's going to eddy around the hard point and deflect off the hard point. And so if you put one rock in, you got to line the whole thing with those rocks. You can't just put one rock in to say, well, I'm getting a little bit of erosion here. I'll just put some rocks down here. Well, you put some rocks down there, and what happens is you just deflect off that and dig a hole over here on your neighbor's side of the channel. So you got to be real careful. We call that common enemy doctrine. Allows you to do that legally, but if you're a government agency, you don't want to go there because you're going to get tagged for making the problem worse. Okay, I think we'll stop there for tonight. Any questions about the assignments? I want you to be reading Chapter 3, doing the Chapter 3 homework questions, doing the cross-section problem. I'd like to get the cross-section problem in by next week at this time so I can show you the solution. I don't want to let that get too stale. If you want to hold off a little longer doing the homework questions, yeah, you can do that. But I'd like you to get those done this coming week if you could. Yeah?
So where do we turn these in then?
You turn them in here at class to me. Put your name on them. Put them up here. Right here. Be great. Nope, no new homework because we're still on Chapter 3.
Are we going to have class next week?
Oh, we don't have class next week because it's Labor Day, right?